We end this section with a talk about sources and a little summary of all the things we talked about. And there is an example in the book, but I decided not to cover it here. So check out the book if you want more examples on some of the things that you can do with this. So it will not be surprising to you that if a sink is both eigenvalues are negative, which is kind of like a phase line, the source will be both eigenvalues are positive. Okay, lambda 1 and lambda 2, both positive. That tells us we are a source. If we have two distinct eigenvalues that are both real. Okay, so we're going to do an example problem to kind of talk about this. Consider a matrix or a system of differential equations that's just E times Y. I asked you earlier how many letters of the alphabet we're going towards. We only do 5. E is our last one. This matrix might look familiar. You could pause the video and find the general solution if you wanted practice, or you could just get it from me. It's K1 e to the 4t times 1, 1 plus K2 e to the t times negative 2, 1. That's the general solution. We can see our eigenvalues. We can see our eigenvectors, right? There's a 1 right here. And we have the general solution. We could plot the straight line solutions. We could do the same kind of analysis. You don't need to be able to plot super nicely by hand. You should be able to plot the straight line solutions and the general behavior, but you don't have to do that analysis of like, oh, this is like a quartic function. You just need to kind of get the idea that, yeah, they're going towards the origin. They're going away from the origin, or they're saddling apart. So let's see what this looks like. So we'll use this plotter, and we have 2, 2. Ooh, look at that spiral. What is that? The answer is you're gonna have to wait. That's not in this section. All right, and then the next one is 1, 3, like so. And we can see something that looks a little interesting. We see that the eigenvectors here, they're both pushing out. And we see some interesting behavior of solutions. In fact, I could draw the phase portrait for this quite simple. All I would have to do is change all these arrows, because this is actually almost the same exact phase portrait as what we did with a source. And you'll notice that the matrix is actually just the opposite of the other matrix. Sources and sinks look the same. You just flip the direction of time. Okay? So everything, that's why the sources is only half a video, because we've already done it. Source is the same as sink. You can write that down. I'm not going to. Sources are the same. I should. Sources are just like sinks, but in reverse time. So flip the arrows. But they look the same. Everything that we talked about for sources goes for sinks. And again, this right here is just the negative D matrix from the previous video. And that's kind of it for sources. That's it. Let's summarize everything. We're going to make a big table. All right, but first, one quick comment. All right, if we have, because remember this whole section is for a specific subset of differential equations, dy dt equals a matrix times y. Right, if we're in this specific subset of systems of differential equations, and A, right, has 2 distinct real eigenvalues, lambda 1 and lambda 2. We're going to be able to say some things. And remember, what happens if we don't have 2 distinct real eigenvalues? We'll talk about that later. In the next section, we talk about complex eigenvalues. Section after that, repeated real eigenvalues. All right, so if this is the case, then there are two straight line solutions along the eigenvectors. I should have written that they're eigenvectors. And specifically, the equilibrium 0, 0 is going to be one of these kinds of equilibria that we talked about. So, can I fit all of this in one page of a table? I have no clue. But we're going to try. Okay, can I draw a straight line? I don't know. So we're going to say, okay, we're going to look at the sign of our eigenvalues. We're going to look at classifying our equilibrium of 0, 0. We're going to look at the long-term behavior and here's the part that I'm not sure about. I want to draw you a picture, a little sketch. Okay, like what it looks like. So the first case is what we talked about, where one of these is negative and the other's positive. Right? If one's negative and the other's positive, what kind of equilibrium do we have? We have a saddle. The long-term behavior, well, let's start with a sketch actually for this. Right? Remember, if we had a saddle, that was like something like maybe this is, one thing, and maybe this one, maybe this one behaves kind of like it's going towards equilibrium. This one's getting pushed away from the equilibrium, right? Then we had these solutions that were kind of hyperbolic in a sense with this sort of situation for our saddle point. And the long-term behavior, notice that as long as, like, if we start upon this like stable, well, I shouldn't say that yet. Saddles are unstable. Well, we'll talk about that in a second. If we start on this line, we go towards the equilibrium. Every other place is going to go off to infinity. All right. So most solutions come from infinity. They veer close to the origin and then go back to infinity. All right. And they approach close to one line and then veer off towards the other. So close to 0, 0 along one line, and then go back to infinity along another. That's the behavior of this sort of system. Now, if they're both negative, then we have a sink, which is what we're going to call a stable node. You might say, Jason, shouldn't a saddle be a stable node? You see saddles in stables all the time. Ha ha ha. No, saddles are unstable. Okay, why do you need a saddle if the horse is in the stable? It's been a long day. All right, so what happens in this situation? Well, we had a picture of this situation too. If we had a sink, right? Again, maybe we have, different eigenvectors along these lines. It's a sink, so they're all going towards the equilibrium, right? And then it'll approach closer to one than the other. So like that'll be one solution. That'll be another solution, right? It always approaches faster towards one than the other. Which one? Well, I'll tell you. Solutions, again, most solutions, there are exceptions. All right, if you're approaching along one of these eigenvector lines, most solutions tend to the origin along V2. So it's always the eigenvalue that's closer to 0. Because the bigger eigenvalue, this is a bigger negative, The bigger eigenvalue, that disappears really quickly. So most of the time you're going across along the eigenvector that has a weaker eigenvalue in a sense. All right, so to be clear, right, this is our V2 in this situation. This is our V1. The V1 component decays much faster, so we're left approaching along the V2 component. It's easier to see if you have like your eigenvectors lie along the X and Y axes. And finally, we have something very, very similar for sources. Again, we'll let lambda 2 be the one that's closer to 0, and lambda 1 be the one that's further from 0. This will be a source. It's what's known as unstable. And we're going to say the exact same thing, just opposite. Right? Most solutions go to infinity. Again, except if you're at an equilibrium. If you're at the equilibrium, you don't go to infinity. And then you're leaving in the direction of V2. So I'll scroll down so you can actually see. All right, so we can really draw the exact same picture for sources. Right, same V2, but now V2 is going away from the origin. And we can do the same V1, but again, now V1 is pulsing away from the origin. And our plot, again, is also the same. You're just now getting away from the origin instead of towards the origin. And specifically the way that you're getting away from the origin, you're approaching along V2. Because V1 is growing much faster, so the V1 component will grow much faster in the long run, yeah. But when you're close to 0, it'll be the opposite. So that's pretty much what we have. The last thing to comment on here for this summary is, why is it called stable and unstable? It has to do with small perturbations from the equilibrium. Like, let's look at all of these pictures, and I'm going to zoom in so you don't have to squint. Right? All of these pictures, maybe not quite that zoomed in. In all of these pictures, think about the equilibrium. They all have an equilibrium, right? They all have an equilibrium at 0, 0. Every system of this type is going to have an equilibrium at 0, 0. And if this is our stable node, our sink. If you are at this equilibrium, you're going to stay at that equilibrium forever. But let's say something happens outside of your system, and it kind of bumps you a little bit. That's no problem. You're going to just slink right back to that equilibrium. So over time, no harm, no foul. It's pretty stable. A little bump, you come right back. Over here, if you're at this equilibrium, if somebody bumps you a little bit, you are going off the deep end. Off to infinity, right? So this is unstable. And sometimes I have days where I'm feeling unstable, where I'm at equilibrium, and just a small thing happens, and then it shoots me off. And this is also unstable as well, because if you're here and you get bumped, there's one specific place you could get bumped. Right? Along this line, if you get bumped, you'll come back just fine. But almost everywhere, right? There are infinitely many directions that you could get bumped. Only one of them is stable, so we say it's unstable. Everywhere else you get bumped, you're going to start zooming off. You get bumped over here, you're going to start zooming off. It's unstable. That's where that comes from. There's another example in the book if you want to see how this is all used in one final example. I didn't find it very useful, so check that out if you want. I think we have enough videos for these sections. That's pretty much it. Hope you're enjoying chapter 3. Next section is where things get really wild. So hope you enjoyed the break. We have complex eigenvalues in the next section, and that'll be fun, but that's for another day. Unless you want to get started early, in which case, cue it up right now. Bye-bye.